Okay, the last time we discussed Poisson's and Laplace equations, and today we will discuss some boundary conditions on them. The term boundary condition is a bit, you can say, fancier, but it is actually the limiting conditions that when you solve an equation, then their solution is not a perfect unless and until you put the boundary conditions and then you put the limiting conditions on them. The limiting conditions are like according to your geometry, that what's your geometry is. Like you are having threads, and those threads you consider as differential equations. From those threads you actually make a cloth. So that cloth making is your solution of differential equation. And then you cut that cloth according to your geometry and you sew it. And then it is your clothes that you are wearing. So according to your geometry, that cloth has transformed into another shape. And these are called the limiting conditions. These are called the boundary conditions. These are called the conditions that you apply according to your given geometry. And then it is the perfect solution. Right? You got the idea that what is a differential equation, what is the solution of differential equation, and then how to apply limiting conditions or boundary conditions of that equation, and you get a perfect solution of that according to your geometry. So, threads, you made a cloth from it, and that cloth is meaningless unless and until you cut it according to your geometry dimensions. And then you just wear that thing. That's a perfect solution of that. So, we discussed the Poisson's and Laplace equation. Okay. The Poisson's and Laplace equations. You know, the Poisson's equation was that del square phi is equal minus 4 pi k rho of x. So I write 4 pi k rho, and if I am in a region where rho is equal to 0, then del square phi will be equal to 0. This is the Poisson's equation and this is the Laplace equation. Now, we will have to solve this equation. And to solve this equation, what will be the solution of it? Solution of it will be phi of x. Means when we will solve this equation, then the solution of it will be phi of x. Once we find this phi of x, then our solution will be ready. And then on this solution, we will apply our limiting conditions or boundary conditions. So, we just first clear some mathematical things which are necessary for understanding all of this. Like, let's say I'm having an equation of a straight line which is y equal 3x plus 2. Now, I know that this is the independent variable, this is the dependent variable, this 3 is the slope of it, and 2 is called the y-intercept because this 2 is coming on this side. So it will be y minus 2. Means I can write this is y minus 2 equals to 3x. So this 2 is called the y-intercept. But if I find dy by dx, then I will get what? 3. And if I am having another equation which is equal 3x plus 10, for example, and I find its derivative dy over dx, then this is equal to 3. Now the question is that whether this straight line and this straight line are the same. The slope of the straight lines are the same, but the straight lines are different, right? Means the straight line, if this is x and this is y, so if this is 1, 2, 3 and 4 and 5, let me just subdivide them so that I can plot the other one as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and then 11 and so on. Now I am plotting this straight line. So this is 8y minus 2. So it means it is touching the y-axis at this point. And what does it mean? Slope 3 means that on y by x will be equal to 3. Means for x equal to 1, y will have to go 3. So it is 3. So it will be somewhere here. And this is that straight line, right? But now, if I say that this y, this one, 3x plus 10, then I will have the straight line like this. Both the straight lines are sharing the same slope, but they are different. But now think of this thing, that when I will integrate this one, or first integrate this one, then y of x will be equal to 3x, right? And if I integrate this one, y of x will be again equal to 3x. So I am missing something. The reason is that I do integrate this one, but these are not the definite integrals. They are the indefinite integrals. If they will be the definite integrals, then there will be no constant of integration. And here will also be a constant of integration. So if I want to have the exact solution of this straight line, I will have to determine this constant. Otherwise, I will end up with another straight line, which will have the same slope, but it will not be exactly that straight line. Clear? Yes. So for the indefinite integrals, we will have to find this constant. But how we will find this constant? We will need some limiting conditions, we will need some boundary conditions. There will be some geometry, and then geometry will actually give us this value. It will tell us that a certain geometry is having this equal to 2 and this one equal to 10. Got it? So this is where our boundary conditions are arising. You go to any subject of physics or engineering or mathematics, then you will have to use the boundary conditions according to the geometry. Right? You know, every one of you, if they are, you can say, of reasonable height, then they are just buying 5 meters of clothes. But who is defining the geometry? The tailor who is sewing those clothes, he cut it according to your geometry. Then they are called your clothes. They are no more cloth, they are your clothes, right? So the geometry is, unless and until you don't have a definite geometry, you cannot say that this is the exact solution of the equation. This is not the exact solution of the equation. This was a differential equation. This was a differential equation. Here is an undetermined value. We will have to determine this value first. And this value will be given by geometry of our system. Clear? We call those limiting conditions as the boundary conditions. Means there will be a surface. That surface will have some definite value of some, let's say, electric field or potential. Now we will have to solve this equation. So after the Laplace and Poisson's equation, we wrote few more things, and those were that rho of x is equal to q delta x minus x prime. We wrote this one. We wrote that the potential pi of x is equal to kq 1 over x minus x prime, and del square of 1 over x minus x prime is equal to minus 4 pi delta x minus x prime. Means putting just the value, you will get this thing, and then I will write the relation that we reached the Green's theorem. The Green's theorem was that the solution of this potential, means the solution of the Laplace equation, will be equal to a volume integral d cube x prime k rho of x prime by x minus x prime plus 1 over 4 pi common is a whole and surface integral, and this surface integral is also common, and we have 1 minus x minus x prime curly phi by curly m prime minus phi of x prime curly by curly m prime and 1 over x minus x prime, and this is dA prime. Now we know about few things over here, that what we included in this one. This one is a charge distribution, means charges are defined somewhere, their distribution is defined somewhere. This term we call that it is a boundaryless term, means it needs no boundary. No boundary required for this term. Because charge distribution is already given to us. When charge is given to you, then you can calculate the potential from it. But sometimes the charge distribution is not given to you and you will have to solve the potential problem. You will have to solve the Laplace equation. Then how you will be able to solve? You need two boundary terms there. In the first term, we have the space derivative of potential, while in the second term, we are having the potential itself. So here it is the potential, and here it is the space derivative of the potential. So it is actually the electric field. So here is the electric field, and here is the electric potential. So we say that the first term is actually electric field on a boundary. It will be specified, means it will be one of our boundary condition or limiting condition. And this one is that the electric potential is specified on a boundary. Okay, if these things are clear to you, then we will proceed to the boundary conditions and the uniqueness. The boundary conditions and uniqueness. What is meant by the uniqueness? Uniqueness means you are having a certain region, and in that certain region you find the potential, for example, or you find the electric field. What surety is that the electric field or the potential will have only that value. Another value is not possible. What surety it will be? Means in a given region, you find the potential value, that potential value will be the same in that region. There will be no other value possible. And this is called uniqueness. We say it's this person is a unique person, means there is no other person like him. So this is uniqueness, means there will be only one solution over there. This is uniqueness, and the boundary conditions, then there are in mathematical methods of physics, you would have studied that there are actually three boundary conditions. The very first condition is the Dirichlet boundary condition. Second boundary condition is the Neumann boundary condition, and the third boundary condition is Cauchy boundary condition. The Cauchy is also called mixed boundary condition. But in electrodynamics, the mixed boundary condition is not, you can say, according to our geometry. Only the first two boundary conditions are according to our geometry. The first one, which is also called the first boundary condition, it is the Dirichlet boundary condition, while the second boundary condition is the Neumann boundary condition. You have studied this thing in mathematical methods of physics. You would have studied this thing in basic electrodynamics or introductory electrodynamics. And this you have done in quantum mechanics as well, in thermodynamics. Sometimes they have different names, like the first boundary condition and the second boundary condition, but they are actually the same conditions, but in different subjects there, you can say form changes a little bit. Like the very first boundary condition, whose name is the Dirichlet boundary condition, is actually the fixation of the actual value of the function on the boundary, right? You are fixing the actual value of the function on the boundary. This is the first boundary condition. While the second boundary condition, which is the Neumann boundary condition, is fixing the space derivative of that function on a boundary. Clear? One is the function itself, the other is the space derivative of that function. Or if you are easy with the space derivative, then it's just a derivative of that function. Let me remind you this thing, that in quantum mechanics, you say that psi is continuous on a boundary. You say like that. When you solve the Schrodinger wave equation is what? It's a second order differential equation. You solve the second order differential equation and then you apply boundary conditions on them. Now the boundary conditions will be according to a given geometry. If the geometry is a Finite square well, then you say that the potential is this much on the walls and inside it is zero. So you get some wave function pattern like half wave, then full wave, then 1.5 wave, and so on. You get their probabilities as well. Or if it will be a free particle, then that is having some other, you can say, boundary conditions, like when they are striking a boundary, some of the waves will, you can say, bounce back, which you call the reflection coefficient, you calculate. Some will transmit, you call the transmission coefficient. In electromagnetic waves, you do the same as well.